Hello everybody, thank you for joining us today. My name is Willem and today we're going to be looking at nuclear equations. So some of our learning objectives are to be able to write and interpret nuclear equations for all alpha decay, beta decay and also gamma decay. So if you're ready, let's get right into it. Okay, to start off, let's have a look at the alpha decay of uranium-235. As always, we have our symbol over here, which is, the top number is the mass number, which remember is the number of protons plus number of neutrons, and then the one below is the proton number, or rather atomic number, and that is just the number of protons. Okay, so to actually write our equation, all we do is the actual element that's decaying, then an arrow away, and okay, so I told you that this is alpha decay, which means that an alpha particle is released. So we can either use that for alpha, right, so the Greek symbol alpha, or we more likely use helium. He, because remember, an alpha particle is really just a helium nucleus. So again, we know that the mass of a helium nucleus is 4, 2 protons, 2 neutrons, and so its proton number is also 2. Now, what is the remaining element here? Because remember, the uranium is unstable, so it's decaying into a more stable element. Well, to work that out, there's just a couple of really easy sums we do. So we take away the mass numbers, 235 minus 4, and that ends up being 231, because remember, everything on this side has to add up to everything on this side, right? Conservation of mass. So that is our mass number, and then our proton number is just 92 minus 2, and that ends up being 89. Sorry, no, that just ends up being 90, and that is our proton number. Okay, so then we would look in our periodic table. So, what corresponds with a mass number of 231 and a proton number of 90? Well, we find out that ends up being thorium. So that's 231 and 90. So now you understand alpha decay. Now let's have a look at the beta decay of uranium-235. Yes, the same element can undergo multiple types of decay. So as always, let's remember that that is the mass number, and that is our proton number. Okay, and then we draw our arrow away showing that it's decomposing, and then we draw a beta particle, which can be given the symbol B, but you don't really use that at GCSE. You tend to use this, just a little e to represent it's an electron. Now, what's the mass of an electron? Well, if you remember, I told you that the mass is pretty much negligible, so we actually just give it a mass number of 0. Now, what is the proton number? Now, if you also remember, I told you that the proton number is really actually just a positive number to represent positive charge. But we know that an electron, which is what a beta particle is, a high-speed electron, has a negative charge. So its proton number actually ends up being -1. Okay, so now if we remember that when a beta particle, a high-speed electron, is ejected from the nucleus of our element here, so in this case uranium-235, a proton turns into a neutron. So really, a neutron turns into a proton to balance out the fact that a negative charge has just left, right? So a positive has to increase. So we don't see a decrease in our proton number, we actually see an increase. So it actually ends up being 92 minus -1, and remember, a minus and a minus actually end up being a plus, so it ends up being 92. Oops, let's do that all again. 92 plus 1, that ends up being 93. So that ends up being the proton number of our new element. And the mass number is just 235 minus pretty much no mass at all, which still ends up giving us the same mass number. So that element, if we look on the periodic table, ends up being neptunium, which is 235 and 93 protons. So now you understand beta decay. Okay, now questions involving gamma decay are pretty rare, but they do crop up, so it's a good skill to be able to tackle them. As always, we have our mass number, and our proton number. Then we have our element decomposing, and all it decomposes into, all that is released is a gamma ray. Now, a gamma ray is just a ray of light, so that means technically it has 0 mass, and because it's also a wave, it also has 0 charge, so it has 0, 0 for both of these values. So when gamma decay occurs, actually the element doesn't change at all. it stays the same, because remember, a gamma ray is just a ray of light. Sorry, a beam of electromagnetic energy released from the nucleus, which just carries away excess energy. It doesn't actually force a change in the actual structure of the nucleus itself. So we end up with the same element, just this element now has a little less energy than it initially did, and that extra energy is released as a packet of energy through the gamma wave.